Okay, so Leetcode practice time. In this video, there are two goals. So the first one is to see how to solve this problem and put in some solid code. And the other one is to see how to behave during a real interview. What is the process we need to follow during a real coding interview? So let's get started. Remember, always the first step in a real coding interview is to try to understand the problem. If there's anything that is unclear to you, please bring up the questions to clarify, to let the interviewer clarify, and also think about the edge cases that you need to take special care of. So let's take a look at this question. So design, add, and search word data structure. So design a data structure that supports adding new words and finding if a string matches any previously added string, and implement the word dictionary class. So this is a constructor, and add word as word to the data structure. It can be matched later, okay? Search word returns true if there is any string in the data structure that matches word, or false otherwise. And the word may contain dot, and dot can be matched with any letter, okay? So let's take a look at this example. We are going to add bad, dad, mad, pad, bad. Okay, so we add three things: bad, dad, mad. And then we search pad, returns false, bad returns true, dot ad returns true because it matches bad or dad or mad. So b dot dot returns true because it matches bad. Yeah, it matches bad. Okay. So let's take a look at the constraints. So the word length is between 1 to 500. It means we are not adding any empty words, which is good. So let's see. Word in add word consists lowercase English letter. Okay, search consists of dot or lowercase English letters. Okay, so the word only consists of English letters in both add word and search word. And at most 50k calls to be made to add and search. So I think we are pretty much clear about what the question is asking us to do. So the next step is about finding a solution. So for the finding solution part, I think there are two ideas in my mind. The first one is to use a try data structure to solve this problem. So if you don't know what try is, I would encourage you to Wikipedia what it is. So essentially it is a kind of tree, and the tree is not binary tree. It has multiple, so each node can have multiple children, and each children essentially is a character. So for example, for this one, for the bad, dad, mad, from the root, there are three children, to B, D, and M. So yeah, so that's essentially what the try is. So if we leverage the try data structure, I would say for the runtime for add word, it is going to be all of n. So suppose n is length of the word. And for search word, suppose it's a regular word without any dot. So without dot, then it is all of n as well. But if there is any dot, the worst case could result in on for no dot words. So if there's any dot, worst case, if there is dot, then worst case is could be the size of the entire tree. So we end up searching the entire tree. Suppose it is some word like combined by all dots, then that's the worst case. We end up searching the whole tree. Worst case. So that's the first thing I can think from the top of my head. And the other thing is we could enumerate all the possible strings when we add words. So suppose we add let's say add, then we are going to add the first one is add, the second one is dot d, and then a dot, and then dot dot. So we enumerate all the possible matching patterns when we add word into a hash set. So this function, for this one, the runtime so the time complexity for add word is 2 to the power of n is the length of the word, and time for search word is going to be constant. And also space wise, it is going to waste more space at the same time, because we need to enumerate all the possible patterns for the words. So I would say definitely bring up the question, what would be the pattern for the API call? Is it more on the read heavy side or write heavy side? It's read heavy or write heavy. So read heavy means we just keep searching without doing too much as. But for write, it means we are going to call the add word API more frequent than search. So I would say, since the word length could be up to 500, I would say it is better for us to go with the try approach from the space wise, due to the concern of the space. So let's get started with the try solution. So we are going to write some code with the try solution. So after you discuss the pros and cons, different options for the solution, and you get an agreement about which solution you're going to go with, it's time for you to do some coding. So for code input, we care about your correctness and your code readability, and of course the speed is a concern as well. So let's get started putting some code. So first of all, we are going to define a class. Let's say it is try node. So our try node, we will have, first of all, we will see whether it is a word, so it is word or not. And the other thing is we need to have a hash map, and the key, of course, is the character, and the value is the corresponding child node. So let's see, I would say this is children, and let's give it a constructor. Try node, so is word, and also just is word. So is word is equal to this dot is word is equal to is word. We are going to initialize the children map. So children would be equal to new a hash map like this. Okay. So we will define a member attribute, which is, let's say, it's private try node root. Okay. So at the very beginning, root would be equal to new try node as false. Okay, so for add word, it is pretty clear. We just go through the corresponding branch and try to expand it, expand the current tree. So let's see, for I is equal to 0, I is smaller than word dot length plus plus I. So car c is equal to or.car at I. So okay, so first of all we need to see try node. First initialize as root. Okay. Okay, so it's initialized as root. Okay, so if node dot contains if node dot contains, okay, so if node we may need to have it as public as well, make it as public. Okay, so if node dot children dot contains key C, so if it already contains a key, then it means we can go forward into it. So C is equal to node is equal to node dot children dot get C. Okay, otherwise it means it doesn't have the corresponding node corresponding child node. Then we need to say, okay, tree node new node is equal to I'll say that, so it would be new tree node, and first we initialize it as false, and then we will put node dot children would be equal to the new node. Okay, the children, okay, we should put C as a new node. Okay, it doesn't contain this one. Alright, so I think we are good going through this, and at the end we will say node is equal to, and also node is equal to new node. So at the end we need to set node dot is word is equal to true. So yeah, so that would be pretty much it. Let's do some sanity check. So after you're done with coding, you need to explain how this piece of code is gonna work by using going through a simple example. So let's say we add a simple word. Let's say we add. So if we add, first of all, we have the root, and the C is equal to the current character is equal to A, and the node.children doesn't contain A, thus we are going to initialize a new node with a new node and put the key as A, value as a new node, and node is set to the new node. Then when it is D, and we see that the children, again, it doesn't contain the D child, so we are going to initialize a new node, put character as key as D and the value as a new node into the children map. Then we go through, and node is equal to the new child node. Okay, and then finally we said the is where that's true. Okay, so I think it should work. Let's go through the next part, which is the search part. So for the search part, it is a little bit special when we have the dot, because if it is a dot, then we end up searching all the children. So let's see. So we would define, I would say we need to define a helper function, which is, so we will say private boolean search helper So we are going to search the word, and we will have the corresponding index of the character we are currently searching. So with this one, we will return search helper word, and starting from 0. So if car C is equal to word dot car at index. So this is a current character. So if C is not equal to dot, then it means it is a regular thing. It's a regular thing. Okay, so I think we also need to see the current try node we are looking at. So we are going to pass the root here. Alright, so if node dot children dot if dot contains key. So if the children doesn't contain the key with the current character, that means we need to return false, because we don't have the corresponding child for the current node we are currently visiting, which means the word is not, we have never added the word before. Otherwise, okay, so I think we need to define the exit as well for the recursion. So if index is equal to word dot length, if it is equal to word dot length, let's see, if it is equal to word dot length -1, okay, so it means it is an ending character. So we are going to say, actually, let's see. So if it doesn't contain the corresponding character, then it means, and if the index, the ending character is the end of the word, then okay, so now the children contains the corresponding character, and it is the last character within the word. Then we are going to say, okay, return node.children dot get C equals to dot is word. So if is word is true, then it means it is a word. Otherwise, it means it is not a word we have ever added. Because, for example, if we have bad and if we search for BA, we shouldn't return true. So yeah, that's essentially, even though there is a node, but the corresponding node is not a word. So that's what we were talking about. So if it's not equal to okay, and if it doesn't contain C, if it is the end of the word, or otherwise, it means it's not the end of the word, and we also have the child. So we are just going to go to the corresponding node. So we are going to say, okay, search, return search, helper word index +1, and node dot children dot get C. Okay, and that's it. So otherwise, it means it is a dot. So the dot means we need to search for pretty much all of its children. So we are going to search all of its children. So we are first going to define Boolean contains word as false. Not really. So we are going to say, okay, we iterate through all of its children. So we say for try node child is equal to node dot children. So if search helper word and index plus 1 no so it means it is a, so if it is a dot, so if it currently is a dot, then it means we don't need to care too much about it. So if it is okay, so after that we need to say it is a dot. So if it is a dot and if index dot is equal to word dot length minus 1, that means it is the last thing. It is the last thing, or the last character within the word. Then we need to try to return. We need to try to see node dot. We need to return node dot children. If it is the last one. So if it is the last one, we just need to see whether any of the current children is word is true. Sure. So if search helper alright. So if it is a dot, then we go to the corresponding child and see, okay, if it's the so regardless, yeah, so if it is a child, no. So if it is the last character, and if it's the last character, we don't really need to compare the value of the corresponding node. Okay, so if search helper word index plus 1 and the node dot child, we just return true, and finally we return false. So the thing I'm thinking about is what if it is the last index, the last character of the word, and the node, the last character of the word, and what we are searching for is a dot. Then I think we don't have the exit for that one at this moment. So if it is a dot, then if it's not a dot, then we return. Yeah, so we haven't defined that. So how to do that? Alright, so I think that means if index is equal to word dot length, we will need to see return whether return node dot is word. Okay, so the thing is this: if it's not, so if the last character is not a dot, then it is never going to reach this condition. So the condition to reach this one is it is that the condition to reach this is the last character is not a dot when we search. So let's see if we can simplify this this approach. So if it is children.sc, so actually don't need to do this, because this one has already been taken care of by this if condition. Okay, so if index is equal to word.length, then node dot is just return node dot is node, and we get the current character. And if it is not a dot, then we need to see, first of all, we need to see whether any of the child is, if the current node has a child with the character as C. Otherwise, we need to return false. If yes, we just go to the corresponding pass to finish the searching. If it is a dot, then it means we need to search all of its children, and if any of them return true, then we return true. Otherwise, we return false. Okay. Yeah, so I think that's pretty much it. So let's again do some sanity check by going through the code. So for example, we have already added 3 words. Let's say we have added bad, dad, let's say just bad, and B. So let's say currently we search for let's say we give a regular search. Let's say we search bad. So first of all, it is a root node, and the index is 0, and index as 0, word as search for word as bad, index 0, root node is equal to root. So first of all, we are going to go to the, so let me draw something to explain better. So it is B, then it is A, and E, and this one, it has a child which is the D, and this one has 2 children, the D and the E. Alright, so first of all, it is the root node, and the root node would be separately. It's a root node. So we are going to see, okay, so the first character is B. It's not a dot. Then the corresponding children contains B, and we are going to search for the rest of the word, starting from index plus 1, which is 1, and we go to the corresponding child, which is this B, and then we see the current character is A, and it has the corresponding children, and we are going to go to the corresponding pass, and then similarly for the last character for D, and then we are going to go to so first of all, so I think so that's just better. So first, it is going to search bad with index as 0, and it's the root. Okay, and then we are going to call search bad and 1 with a node B, okay, which is this one. Then we are going to call search bad and 2, and it is going to be A, search the node A. And finally, we are going to say, okay, search bad and 3, and it is node D, which is this one. And it appears that this one, the A word, is set as true, and then we finally return true. Yeah, I think it should work. And similarly, it is let's say if we search for B, let's say if we search for BE dot. So the calling stack is going to be first BE dot, and then root, and then the next one would be b e dot 1, and it goes to the node b, which is this one. And then we are going to call search be e2 012, which is we are at the e node. And then it's the time we encounter the dot, then we are going to search all the children of the e. So it contains two things, d and e. And we are going to call search be dot and 3 and node d. So first of all, we search for node d, and it says that it's already a word, and then we just simply return true. And we don't need to search the other child of this node e. So I think it should work. Let's give it a shot. Okay, so some compile actual. So node dot children. I think we define the children here, right? Children. So for each not acceptable. Oh, okay. Dot. Okay, it is the key set. Key set. We just get the key set, and which is a character. Okay. Okay, so this is a character, and then we are going to search word index +1, and this is going to be the children node we are trying to search for. So it would be node dot children dot get c. Okay, so node dot children get key set, and it's all the keys of the children node, and then it is a corresponding children node. Okay, yeah, sure. C is already defined. Okay, so let's see, just key. Okay. It's weird. The local variable should work, but yeah, let's see. So it's accepted. Then let's submit this piece of code. Okay, so it works very well. So remember, the last step for testing, after you do sanity check, checking all the logic by going through an example for all the APIs, then we still need to come up with some other test cases to try to increase the test coverage. So I would say for add word, we definitely add some words there, and for example, if we add the BAD, BED, BEE into by calling the add word, for search word, I would say definitely set a search for a regular word which is going to return true, search for a regular word which is going to return false, and also search for some pattern which is going to return true, search for some pattern which is going to return false. And also another thing is worth to mention is, for example, if we just search for BA, for this one it should return true. Sorry, it should return false, even if there is a corresponding node there, but its word is set as false. So that one we also need to take special care of when setting up the test case. I would say if you consider all the things, all the branches properly, that will be good enough for the test case coverage. So that's it for this coding question. And if you like this video, find it a bit helpful, please give me a like, and I'll see you next time. Thanks for watching.